Professor J.Guttag, two more quick things.
Don't want your image recorded and posted on the web. You're supposed to sit in the back 3 rows.
Thank you, I forgot.
The web, you're supposed to sit in the back 3 rows.
I think you're all very good looking.
Because the camera may pan. I'll turn around, so if you wanna, you...
I'll turn around, so if you want to, move to the back, I won't.
No, move to the back. I won't see who moves.
Won't see who moves. All right, great. Thank you, John.
Great. Thank you, John. Professor J.Guttag. So that the other thing I wanna mention
The other thing I want to mention is recitations are also very important. We will be covering material and recitations that are not in the lecture.
is recitations are also very important.
Not in the reading, and we do it.
The lectures not in the reading, and we do expect you.
Expect you to attend recitations. Great.
Great, Professor E.Grimson. Great.
Thanks, John.
Thanks, John.
Any questions about
Any questions about the administrivia?
administrivia? I know it's boring.
I know it's boring, but we need to do it. So you know what
But we need to do it so you know what the ground rules are.
the ground rules are.
Good. Okay.
Good. Okay.
Let's talk about computation.
Let's talk about computation.
As I said,
As I said, our strategic goal, our tactical goals are to
strategic goal, our tactical goals are to help you think
like a computer scientist. Another way of
like a computer scientist. Another way of saying it is
saying it is, we want to give you the skill so that you can
give you the skills so that you can
make the computer do what you want it to do.
do what you want it to do. And we hope that at the
And we hope that at the end of the class, every time you are
end of the class, every time you're
confronted with some technical problem, one of your first
one of your first
instincts is gonna be, how do I write the piece of code
going to be, how do I write a piece of code that's going to help me solve it?
that's gonna help me solve that?
So we want to help.
So we want to help you think like a computer
You think like a computer scientist.
scientists. All right.
Right? And that
And that is an interesting statement.
is an interesting statement. What does it mean to think?
What does it mean to think like a computer scientists?
Like a computer scientist. Well, let's see.
Well, let's see.
Primary knowledge you're going to
The primary knowledge you are gonna take away from this
take away from this course is this notion.
course is this notion of computational problem solving.
Computational problem solving.
This ability to think in
computation.
computational modes of thought.
Modes of thought. And unlike
And unlike in a lot of introductory courses, as
In a lot of introductory courses, it's a
consequence, having the ability to memorize is not
ability to memorize is not going to help you.
gonna help you.
It's really
It's
learning
really learning those notions of the tools that you
those notions of the tools that you want to use.
want to use.
What in the world does it mean?
What in the world does it mean to say
It's a
computational mode of thought?
mode of thought. Sounds like highfalutin.
It sounds like a highfalutin phrase you use when you are
Phrase you use when you're trying to persuade a VC.
trying to persuade a VC to fund you,
To fund you. Right? So
right?
to answer this, we
So to answer this, we really have to ask a different
really have to ask a different question.
question, a related question. So what's computation?
Related question. So what's computation? Like a strange statement.
It's like a strange statement, right?
Right? What is computation?
What is computation?
And part of the reason for
And part of the reason for putting it up is that I want
putting it up is that I wanted as much
as possible answer that question by
as possible answer that question by
separating out the mechanism, separating out the mechanism which is the computer from
now the mechanism, just the computer, from
computational thinking.
Right? The artifact
The artifact should not be what's driving this.
should not be what's driving this. It should be the notion of
It should be the notion of what does it mean to do
what does it mean to do computation.
computation.
Now to answer that,
Now to answer that, I'm gonna back up one more level.
back up one more level. I'm going to pose what
And I'm gonna pose what sounds like a philosophy
sounds like a philosophy
question, which is what is knowledge? And you'll see in
what is knowledge? You'll see in about 2 minutes
about 2 minutes why I'm gonna do this.
what it is. But I want to suggest that
But I'm gonna suggest that I can divide knowledge into
I can divide knowledge into at least
two categories.
categories. Okay, what is knowledge?
Okay, and what is knowledge?
And the two categories
And the two categories I'm gonna divide them into are
I'm going to divide them into
declarative and imperative knowledge.
and imperative knowledge. What in the world is
What in the world is declarative knowledge?
declarative knowledge? Think of it as
Think of it as statements of fact.
statements of fact. It's assertions of truth.
It's assertions of truth.
Boy, in this political season,
Boy, in this political season, that's a really dangerous
and that's a really dangerous phrase to use.
phrase to use, right?
Right?
but it's a statement of fact.
I'll stay away from the political.
I'll stay away from the political comments.
Political comments. Let me give you an example.
Let me give you an example of this.
Right?
Here's declarative statement.
A declarative statement.
The square root of x is that y such that y squared equals x.
Square root of x is that y such that y squared equals x. Y is positive.
Y's positive.
You all know that.
You all know that.
What I want you to see.
But what I want you to see here is that's a
That's a statement.
Statement of fact.
Fact. It's a definition.
It's definition. It's an axiom.
Axiom.
It doesn't help you find square roots.
Doesn't help you find.
It doesn't help you find square roots.
Square roots. If I say x is
If I say x is 2, I want to know what's the square root
2, I want to know what's the square root of 2. Well,
of 2. Well, if you're enough of a geek, you'll say 1 full stop 4 1 5 2 9 or
if you're enough of a geek, you'll say 1.41529 or whatever the heck it is.
whatever the heck it is. But in general, this doesn't help.
But in general, this doesn't help you find
You find the square root.
square root. The closest it does,
The closest it does is it would let you test. You know,
is it would let you test. You know, if you're wandering through
if you're wandering through Harvard Square and you see an
Harvard Square and you see an out-of-work
Harvard grad, they're handing out examples
grad, they're handing out examples of square roots.
of square roots. They'll give you an example and you can
Give you an example and you can test it.
test it to see is the square root of
See, is the square root of 2 1.41?
2 1.41529 or whatever.
529 or whatever. I don't even get laughs at it.
I don't even get laughs at Harvard jokes. John, I'm gonna
Harvard jokes, John. I'm going to stop in a second here.
stop in a second here. All right.
All right, so what am I trying?
All right, so what am I trying to say here?
To say here, it doesn't.
It doesn't. Yeah, exactly.
Yeah, exactly. We're staying away from.
We're staying away from that really quickly, especially
Now, really quickly, especially with the cameras
with the cameras rolling.
rolling. All right, what am I trying?
What am I trying to say?
To say? It tells.
It tells you how you might test something, but it doesn't
You how you might test something, but it doesn't tell
you how to.
how to. And that's what imperative.
And that's what imperative knowledge is.
Imperative knowledge is. Imperative knowledge.
Imperative knowledge is a description of
a description of how to deduce
How to deduce something.
something.
So let me give you an example of a piece
So let me give you an example of a piece of imperative knowledge.
of imperative knowledge.
All right? This is actually
Right, this is actually a very old piece of imperative
a very old piece of imperative knowledge for computing.
knowledge for computing square roots. It's attributed to
For roots, it's attributed to Heron of Alexandria.
Heron of Alexandria. Although I believe that the Babylonians
Although I believe that the Babylonians
are suspected of knowing it beforehand.
suspected of knowing it beforehand.
But here is a piece of imperative knowledge.
Piece of imperative knowledge. Right?
All right.
I'm going to start.
I'm gonna start with a guess. I'm gonna call it G.
With a guess, I'm going to call it G. And then I'm going to say,
And then I'm gonna say, if G squared is close to X, stop.
okay, if G squared is close to X, stop. And return G.
And return G.
It's a good enough answer.
It's a good enough answer.
Otherwise,
I'm gonna get a new guess by taking G, X over.
I'm going to get a new guess by taking G, X over G, adding them,
Over G, adding them and dividing by 2.
dividing by 2. You take the average of G.
Then you take the average of G and X over G.
And X over G. Don't worry about how.
Don't worry about how came about. Heron found this out.
Came about. Heron found this out. But that gives me a new.
But that gives me a new guess. And I'm gonna repeat.
Guess. And I'm going to repeat.
That's a recipe.
Recipe. That's a description.
That's a description of a set of steps.
Of a set of steps. And notice what it has.
Notice what it has. It has a bunch of nice things that we
It has a bunch of nice things that we want to use.
wanna use, right?
Right? It's a sequence.
It's a sequence of specific instructions
Of specific instructions that I do in
that I do in order.
order. Along the way,
Along the way, I have some tests, and depending on the
I have some tests. And depending on the value of that test,
value of that test, I may change where I am in that
I may change where I am in that sequence of instructions.
sequence of instructions.
And it has an end test. Something
And
that-
it has an end test, something that tells me when
I'm done and what the answer is.
I'm done and what the answer is.
This tells you
This tells you how to find square roots.
how to find square roots. It's how to know.
It's how to knowledge.
It's imperative knowledge.
It's imperative knowledge.
Right? That's
Alright, that's what computation basically is about.
what computation basically is about. We want to have
ways of capturing this process.
Ways of capturing this process. Okay, that leads now.
Okay, and that leads now to an interesting question, which
would be
how do I build a mechanical process to capture that set of computations? So I'm gonna suggest that
there's an easy way to
there's an easy way to do it.
do it.
I realized I did the boards in the wrong order here. One of
the ways I could do it is
the ways I could do it is you could imagine building a little circuit to do this. If I had a couple of elements of stored values in it, I had
stored values in it. I had some wires to move things.
Some wires to move things around. I had a little thing.
I had a little thing to do addition.
To do addition. Little thing to do division. And
Little thing to do division. And something to do
something to do the testing. I could build a little circuit.
I could build a little circuit that would actually do
circuit. What that would actually do this computation. Okay? That, strange as it sounds, is actually an example of the...
Strange as it sounds is actually an example of the earliest computers.
Earliest computers, because the earliest computers were...
The earliest computers were
what we call fixed program computers, meaning that they
fixed program computers, meaning that they had a piece of circuitry designed to do it.
Had a piece of circuitry designed to do a specific computation. And that's what they would do. They would do that specific computation.
You've seen these a lot.
You've seen these a lot, right? A good example of this, calculator.
This calculator.
It's basically an example of a fixed program computer.
An example of a fixed program computer. Does arithmetic.
It does arithmetic.
You want to play video games?
If you want to play video games on it, good luck.
It's on it, good luck. You want to do Word?
If you want to do word processing on it, good luck.
Processing on it, good luck.
It's designed to do a specific thing. It's a fixed program computer. In fact, a lot of the other really interesting early ones.
Other really interesting early ones Similarly,
have this flavor. To give an example, I never know
have this flavor. Give an example. I never know how to pronounce it.
how to pronounce this. Atanasov, 1941.
This Atanasov, 1941.
One of the earliest computational things was a
computational things was a thing designed by
thing designed by a guy named Atanasov, and it basically
a guy named Atanasov. It basically
solved linear equations. Handy thing to do if you are doing 1801, all right, or
doing 1801, right, or
1806, or whatever you wanna do those things in.
Whatever you want to do those things in. All it could do though was solve those.
All it could do, though, was solve those equations. One of my favorite examples of an early computer was done by
examples of an early computer. It's done by Alan Turing.
Alan Turing. Time called the Bomb, which was designed to break codes.
Which was designed to break codes.
It was actually used during WWII to break
World War II to break German Enigma codes.
German Enigma codes. And what it was designed to do was to solve that specific problem. The point I'm trying to make is fixed program computers is where we started, but it does not really get us to where.
Doesn't really get us to where we'd like to be.
We wanna capture this idea of problem solving.
Capture this idea of problem solving. So let's see how we'd get there.
So even within this framework of given a description of
this framework of given a description of a
computation as a set of steps in the idea that I could build
a circuit to do. But let me suggest what
a circuit to do it. Let me suggest for you what would be a wonderful circuit to build. Circuit to build. Suppose you could build a circuit with the following property. The input to this circuit would be any other circuit diagram. Give it a circuit diagram for some computation. You give it
to this
to the circuit, and that circuit would wonderfully
And that circuit would wonderfully
reconfigure itself to act like the circuit's diagram.
itself to act like a circuit diagram, which would mean it could act like a calculator,
Or it could act like Turing's bone.
act like Turing's bomb, or it could act like a
Or it could act like a square root machine.
square root machine. So what would that circuit
So what would that circuit look like?
look like?
You can imagine these tiny little robots wandering
Imagine these tiny little robots wandering around, right, pulling
around, right?
wires and
Pulling wires and pulling out components and
pulling out components and stacking together.
stacking them together. How would you build a circuit that could take a circuit,
How would you build a circuit that could take a circuit diagram and
the diagram in, and make a machine act like that circuit?
make a machine act like that circuit?
Circuit.
Sounds like a neat challenge.
Sounds like a neat challenge.
Let me change the game
Let me change the game slightly.
slightly.
Suppose instead I want a machine that can take
I want a machine that can take a
recipe, the description of a sequence of steps, take that
the description of a sequence of steps. Take that
as its input, and then that machine will now act like what?
And then that machine will now act like what is described
Is described in that recipe.
in that recipe. Reconfigure itself.
Reconfigure itself, emulate it however you wanna use,
Emulate, however you want to use the words. It's going to
the words. It's gonna change how it does the
change how it does the
computation.
computation. That would be cool.
That would be cool.
And that exists.
And that exists.
It's called an interpreter.
It's called an. It is the basic heart of every computer.
The heart of every computer. What it is doing
What it is doing is saying, change the game.
is saying, change the game.
This is now an example of a stored program computer.
an example of a stored program computer. What that means
in a stored program computer is
a stored program computer is
that I can provide to the computer as sequence of
provide to the computer a sequence of
instructions describing the process I want it to execute.
Describing the process I want it to execute. And inside of the machine,
And inside of the machine, and things we'll talk about there,
and things we'll
there is a process that will allow that sequence to be executed.
Process that will allow that sequence to be executed
As described in that recipe, so it can behave like any thing that I can describe in one of those recipes.
Right?
All right.
That
That actually seems like a really nice thing to have, and
seems like a really nice thing to have. So let me show you.
so let me show you what that would basically look like.
What that would basically look like. Right? Inside of a
Stored program computer, we would have the
program computer. We would have the
following. We have a memory. It's connected to two things.
We have a memory. It's connected to two things.
Control unit in what's called an ALU, an arithmetic logic.
What's called an ALU, an arithmetic logic
unit, and this can take in input and spit out output.
This can take in input, spit out output. And inside
this stored program computer, excuse me, you have
stored program computer. Excuse me, you have the following.
The following. You have a sequence of instructions.
You have a sequence of instructions.
And these all get stored in there.
These all get stored in there. Notice the difference.
Notice the difference.
The recipe.
The recipe, the sequence of instructions is actually
getting read in.
Getting read in, and it's treated just like data.
It's treated just like data. It's inside the memory of the machine.
It's inside the memory of the machine, which means we have
access to it. We can
access to it. We can change it. We can use it to build new
We can use it to build new
pieces of code, as well as we can interpret it.
As well as we can interpret it. One other piece that goes.
One other piece that goes into this computer. I never remember where to put the PC, John. Control.
Put the PC, John. Control. ALU.
Alus. Separate.
Separate. I'll put it separate.
I'll put it separate. You have a thing.
We have a thing called a program counter.
Called a program counter. And here's the basis of the computation. That program counter points to some location in memory.
Counter points to some location in memory.
Typically to the first instruction in the sequence. And those instructions, by the way, are very simple. They are,
by the way, are very simple. They're
Things like take the value out of two pieces in memory
Take the value out of two places in memory and run them through the
multiplier in here a little
multiplier in here, little
piece of circuitry, and stick them back into
and stick them back into
some place in memory.
Or
take this value out of memory, run in through some
value out of memory, run it through some
other simple operation, stick it back in memory.
stick it back in memory. Having
executed this instruction, that counter goes
this instruction, that counter goes up by 1 and we move
up by 1 and we move to the next one.
to the next one. We execute that.
We execute that instruction. We move to the next one.
The instruction, we move to the next one.
Oh yeah, it looks a whole lot like that.
It's a whole lot like that. Some of those
instructions will involve tests. They'll
instructions will involve tests. They'll say, is something
say, is something true?
true? And if the test is
And if the test is true, it will change the value of this.
True, it will change the value of this
program counter to point to some other place in the memory, some other point in that sequence of instructions. And you'll keep processing. Eventually, you'll hopefully stop and a value gets spit out and you're done.
That's the heart of a computer.
That's the heart of a computer. Now that's a slight misstatement. The process to control it is intriguing and interesting. But the heart of the computer is simply this notion that we build our descriptions, our recipes on a sequence of primitive instructions. And then we have a flow of control. And that flow of control is what I just described. It's moving through a sequence of instructions, occasionally changing where we are as we move around. Okay, the thing I want you to take away from this then is to...
The thing I want you to take away from this then is to think of this.
Think of this as this is, if you like, a recipe.
As this is, if you like, a recipe. And that's really what
and that's really what a program is.
sequence of instructions.
It's a sequence of instructions.
Now, one of the things I left,
Now, one of things I left hanging is I said, okay, you
hanging as I said, okay, you build it out of primitives. So one of
build it out of primitives.
the questions is, well, what are
So one of the questions is, well, what are the right
the right primitives to use?
primitives to use?
And one of the things that would
And one of the things that was useful here is that we
is useful here is that we actually know that
actually know that the set of primitives that you wanna
the set of primitives that you want to use
is very straightforward.
very straightforward. Okay, but before I do though,
Okay, but before I do that, let me drive home this idea of why
let me drive home this idea of why this is a recipe.
this is a recipe.
Assuming I have a
Assuming I have a set of primitive instructions that I
set of primitive instructions that I can describe everything.
can describe everything on, I want to know what can I build.
I want to know what can I build. Well, I'm going to do the same.
Well, I'm gonna do the same analogy to a real recipe.
Same analogy to a real recipe. It's a real recipe.
So, real recipe.
I don't know.
Separate 6 eggs.
6 eggs. Do something.
Do something.
Beat until the
Beat until beat the whites
beat the whites until they're stiff.
until they are stiff.
Do something until
Do something until an end test is true.
an end test is true. Take the yolks of
Take the yolks and mix them in with the sugar and water.
mix them in with sugar and water.
No, sugar and flour, I guess, is probably what I want. Sugar
Flour, I guess, is probably what I want. Sugar and water is not going to do anything.
and water is not gonna do anything interesting for me.
Interesting for me here.
Here, mix them into something else.
Mix them into something else. Do a sequence
Do a sequence of things.
of things. A traditional recipe
A traditional recipe actually is based on a small set of
actually is based on a small set of
primitives, and a good chef or good cook, I should
and a good chef or good cook, I should say, with the best of
say with that set of primitives can create an
primitives can create an
unbounded number of great dishes.
great dishes. Same thing holds true.
Same thing holds true in programming,
Programming,
right?
Given
Given a fixed set of primitives, all right, a good
a fixed set of primitives, a good
programmer can program anything.
can program anything. By that I mean anything.
And by that, I mean anything that can be described in one
Anything that can be described in one of these processes.
of these process you can capture in that set of
You can capture in that set of primitives.
primitives.
Right. The question is,
Right, all right. The question is, as I started to say, is what
As I started to say, is what are the right primitives?
are the right primitives? So there's a little bit of
So there's a little piece of history.
little piece of history here, if you like.
Here, if you like.
In 1936, that same guy, Alan Turing, showed that with
36, that same guy, Alan Turing, showed that with 6 simple primitives,
anything that could be described in a
anything that could be described in a
mechanical process, it's actually algorithmically
process, essentially algorithmically,
could be programmed just using those 6 primitives.
Think about that for a second.
Think about that for a second. That's an incredible statement.
6 primitives.
It says with 6 primitives I can rule the world.
6 primitives.
With 6 primitives I can program anything. A couple of really interesting consequences of that by the way. One of them is it says anything you can do in one.
One of them is it says anything you can do in one
programming language you can do in another programming language. And there is no programming language that is better. Well,
programming language that is better. Well, actually, it's not quite true.
Actually, that's not quite true. There are some better at doing certain kinds of things, but there's nothing that you can do in C that you can't do in Fortran.
C that you can't do in Fortran. It's called Turing compatibility.
It's called Turing compatibility. Anything you can do with one, you can do with another. It's based on that fundamental result. Okay?